Hi, this is Jianqiao. Today I'm going to introduce how we apply hardware and software co-design to accelerate Garbled Circuit for fast and arbitrary private computation. In this talk, you can see how we take the insight of Garbled Circuit as a data-oblivious program to build a novel system that streams the regular and addresses the irregularities by decoupling the program execution and memory access. We eliminate the expensive hardware with a VLIW-like compiler to enable parallel performance. Security and privacy has become a paramount concern in today's digital landscape. Normally, people focus on securing storage and communication through encryption. We can lock our private data in the storage or send them in a ciphertext. But when it comes to computation, encrypted private data must be decrypted to plaintext, which makes the computation a missing piece to enable a true end-to-end privacy. However, with privacy-preserving computation, we are now able to compute directly on encrypted data. This is a strong cryptography technology. Your data will remain encrypted throughout the entire process. There are two major types of private computation. One is secure outsourced computation, for example, homomorphic encryption. You may have heard of it before. Another type is secure multi-party computation, for example, Garbled Circuit, which is our focus today. Both types provide confidentiality, but unlike secure outsourced computation, multi-party computation gives you control over how your data are used. Garbled Circuits support secure computation over Boolean logic. So in the first step, if we transform a function into logic gates, there are two benefits. First, Garbled Circuits support any data type. You can either run integer or floating points. Secondly, it supports arbitrary computation, not only matrix multiplication, but also conditional code. As we mentioned, arithmetic homomorphic encryption is an alternative scheme, but it supports linear functions such as addition and multiplication only, making it hard to build a function such as ReLU in private neural networks. As Garbled Circuit has several benefits, why aren't they widely used today? Because they have a large computation cost and a memory movement. In order to figure out why Garbled Circuit has high computation cost, we need to understand what is included in Garbled Circuit. Generally, Garbled Circuits are encrypted logic gates. In a plaintext, a gate has its input called wire. The truth table represents the gate property. On the other hand, in Garbled Circuit, each bit in the wire will be replaced by a 128-bit label. It can protect your data because only the user itself knows what the label means. Let's transform the bits into labels. Next, there is a double encryption. We use one of the input label as the key to encrypt the output. Then we use another input as a key to encrypt the previous table again. And finally, we randomly shuffle each row. This is our garbled table. So therefore, if someone else wants to evaluate this gate, and if he has the input label, he can use it as a key to decrypt the garbled table. First, he is only able to decrypt two rows. Then he will use another input to decrypt them again to receive the output. Note that during the evaluation, he doesn't know the truth table of the input or output values. That is how your private data are protected. In a word, Garbled Circuit consists of many gates, where wires are the operands and the garbled table is the constant of the gate property. Today, high-performance Garbled Circuits are implemented with AND gate and XOR gate. Garbled Circuit has its challenges. Normal logic operation is cheap, but Garbled Circuits are different. They include symmetric key cryptography, which is AES here, and other operations. Not only does the computation become heavy, but also the amount of data gets higher. Operands become 128 bits, and each AND gate requires a 32-byte garbled table, which makes the memory cost go up to 80 bytes for each gate. And finally, there's a large computation volume. because everything is represented as gates. For example, there are 1.5 million gates in a matrix multiplication circuit. Result shows an average slowdown of 198,000 times compared to plaintext on VIP bench. Therefore, our challenge is how to efficiently schedule such a huge circuit and how to ensure execution not affected by heavy memory traffic. Although it is complex, privacy-preserving computation has a feature that they are data oblivious to guarantee security. The memory access pattern and the program execution are independent of the input data. So it gives us a good chance to apply hardware and software co-design to solve these challenges. We can use a deep pipeline to accelerate each gate and use the compiler to handle the parallelism and all data movement. It could make the performance sensitive to the instruction scheduling, but it gives us a very efficient chip because we don't waste the hardware. The hardware only focuses on its core computation. This is a reminiscent of VLIW-like design, where there are parallel complex pipelines, which are driven by a compiler. For each challenge, we have a unique solution. We start with the hardware. We design a custom logic to speed up the gate computation. In HAAC, we use a deep pipeline called gate engine as the core component. A gate engine can compute a garbled circuit gate in each cycle. We test and validate it as a fixed unit. It achieves a speedup of 95 times than running garbled circuit on CPU. We allocate multiple pipelines to do many gates at once. We also use a network for output fast forwarding to resolve data hazards in or between gate engines. Results shows that 16 gate engines has 12 times speed up than the single engine without optimizing compiler and high bandwidth memory. As we have a fast hardware to compute each gate, we don't want it to be stopped by the heavy data movement. Our insight is to decouple the program execution and data movement to hide latency. HAAC has a unique memory system called SWW to do that. Basically, there are three kinds of data movement. The instruction and garbled table are single-use constant for each gate. So the easy way is to string them to the gate engines. But the wires are difficult because there will be irregular access, and they can be reused by the following gates. Fortunately, we find that a wire tends to be consumed in a short period. So we will succeed if we can cache most recent use wires. But cache has expensive tag and associated lookup. We realize data oblivious and design a smart sliding wire window memory. It has the benefit of cache, but at a cost of a scratchpad. In each gate, we use the wire ID as the address of the wire and store them in the memory. Our idea is to keep the sliding window capturing a range of global wires and move the range according to the program advance. Here, our on-chip memory can store the range from wire 1 to 10. In the next gate, a new generated wires will continuously occupy the new memory space, and finally run out of the on-chip memory. In this case, the new wire number 10 uses the last memory space. So in the next instruction, we don't have space for the new output wire 11. Of course, we can put it to the DRAM, but it will slow down the following reuse. So we decided to move the SWW range forward and reuse the memory space to map these new wires. As we mentioned, garbled circuit is data oblivious, so the compiler will help us to map the wire. For the gate engines, they only need to follow the HAAC instruction to access the memory. That is, in fact, we use co-design to keep the most recent wires on chip. But how about the wire that is out of this range? In this case, it is calling the wire 1, which is not on chip. In HAAC, the compiler will also filter out these out-of-range wires. These wires has a copy in the DRAM. We can push them to the queue in advance. So in HAAC instruction, it will be declared whether you should fetch from SWW or go to check the out-of-range wire queue. In fact, data oblivious doesn't mean everything is regular. There's still random memory access. we use SWW to capture most of the wire reuse. For another small part, which is less than 20%, we use the Q to hide latency. In this way, we totally decouple the gate execution and memory access. Data movement are handled by the compiler, and hardware only needs to focus on computation. Finally, not only data movement, we also optimize the compiler to schedule instructions for parallel execution. EMP-tool is a garbled circuit framework to generate basic circuit. But this baseline circuit has difficulty for parallel process because it tends to put the gates in depth transverse. In HAAC, we analyze the baseline and reorder it according to the circuit level. In this example, we should parallel gate 1 and 4 instead of 1 and 2. And finally, we rename the instructions according to the execution order, because reordering scrambles the gates and the output wires. Renaming is the basis of SWW, as you may remember that SWW needs the continuous address so that it can move forward. As we leverage ILP, with a better memory movement, it can provide us more than 6 times speedup than the non-optimized baseline. So overall, we evaluate HAAC with the benchmarks from VIP bench and achieve a speedup of over 500 times with DDR4 memory and over 2,000 times with HBM in only 4 square millimeter of area. Finally, I conclude our work HAAC, where we use hardware and software co-design to accelerate garbled circuit for faster private computing. Thank you very much, and I'm very happy to take questions.